Hello, this is Jack Jackson. In this video, we're going to talk a little bit about kites. So let's start with this and look at the definition. Here's the definition. A kite is a quadrilateral with two disjoint pair of consecutive congruent sides. So the first thing I want to see is if you understand why the words disjoint and consecutive are important in the definition of a kite. What kinds of things would removing the word consecutive allow? And what kinds of shapes would removing the word disjoint allow? You can pause the video and think about that a minute. Okay, well, consecutive is important because we want the the sides. So, for example, we would like AB and AD to be congruent, not AB and DC, not opposite sides. So here, this one has two pair of congruent sides, but they're opposite. So the word this is okay. This is an interesting shape, but it's not what we want to be a kite. See, we want to eliminate that. Now, why disjoint? Why don't you just say two pair of consecutive sides congruent? Well, this shape right here also has two pair of consecutive sides. We got this pair AD and AB, and we have another pair AB and BC that has two pair of consecutive sides congruent, but they're not disjoint pairs. Both of those pairs include the side AB. And so we want to make sure we eliminate that shape as well. We don't want that to be a kite. So we don't want either one of these things to be kites. Hence, the definition, a kite is a quadrilateral with two disjoint pair of consecutive congruent sides. So the next thing I have here is a task that I'd like you to do. And let's see if we can kind of step through the pieces of this task. But I'd like you to do these yourself before you see me do them. Okay? So for now, we're going to do this in Euclidean geometry, but the task could be repeated in hyperbolic and spherical geometries, or taxicab geometry for that matter, and to see if we would get the same conclusions or not. Okay, so start with a kite ABCD, and we want sides AB and AD to be this congruent, to be the same length, AB and AD. And then we also want sides BC, or CB and CD, to be equal length or congruent. Okay, here I've set it in terms of the lengths, or I could have set it in terms of congruent sides. Okay, so perform this thing. So first of all, you want to make a kite. Well, how do you go about making a kite? There's actually several ways to go at it, but one of the best ways to do it using the definition of a kite is to start by just picking three free points, A, B, and C. Go ahead and make your sides AB and BC line segments. And then use circles in the definition of a kite to construct the final vertex D. And then finish by constructing the remaining sides. Okay, so see if you can do that in GeoGebra now. Press pause on the video and come back when you finish that. Press pause now. Okay, so hopefully what you did is something like this. You start with three free points, A, B, and C. Okay, and I have different labels here, but let's see, I can change the without changing the name of it. I can go to the settings and change the label, the caption on it, to A, B, and oops, A, B, and C. And then use your line segment tool to complete the sides. Why didn't this one change to C? Let's try that again. C. Okay, there we go. So now we have three completely free points. These can go anywhere except to be collinear. Okay. All right, so now where's the point D got to be? On the one hand, it's got to be the distance AB away from A. So it has to be on this circle centered at A going through B. It has to be on that circle. At the same time, it has to be the distance CB away from C. So it has to be on a circle centered at C of radius CB. Well, of course, those are going to meet at point B. And then the other point where they meet is over here, like this. Let's name that point, or at least label it as D. And so there's our final point. So now we have a side here and a side here. And just for emphasis purposes, we can take these two sides right here. I'm going to make it just a little thicker. I'll make them the same color, and I'll actually mark them with a mark that says that they're congruent. And then we're going to do the same thing for these other two sides here. We'll make them a little thicker, and we'll choose double hash for the mark, and maybe, how about a red? So these things we can hide or make dotted or something. Okay, so there is a general kite. So notice that A, B, and C can go anywhere. It can be made concave. It can be made convex. We might have some right angles in it. We might not have. It should be free to go anywhere we want, basically for A, B, and C. You don't want them, of course, to be collinear. But otherwise, we've got a nice kite there. Okay? So that's a construction for a general kite. Okay, how about the next task now? Next, measure the angles and sides of the kite, and then see what you notice about the sides about those things. Okay, go ahead and do that yourself. Press pause now. Okay, if you're back now and you've tried it yourself, it's very important that you try this yourself. I actually already have this thing constructed with the measurements done, so I'm going to go ahead and do this. I'm going to go to Kite, to disjoint pair of consecutive sides that are congruent. Here's one where I've already got the sides measured, and it's constructed more or less the same way as the last one here. Okay, and here I can measure the angles as well. Do you notice anything about those angles? Here I've got them measured in radians. You can measure them in degrees instead. Well, do you notice of the four angles, at least at the moment, we have a pair of congruent angles right here. That's interesting. Okay, but this pair is not necessarily congruent. It might be if it was sort of drawn just right, but you do have a pair that seem to be staying congruent no matter how we adjust A, B, and C, which are our control points for the kite. All right. So of course we have two pair of congruent sides that we knew that was part of our construction, but we also get a pair of congruent angles there. That's kind of interesting. Next, look at the diagonal. What do you notice about the two triangles here? Can you prove your conjecture? Well, hopefully you notice that these two triangles are congruent. How could you be sure? Well, you see that that side is congruent to itself. These sides are congruent to each other, and the two red sides are congruent. So by what theorem? SSS, side theorem. These two triangles are congruent. Well, among other things, that proves that these two angles really are congruent right here at B and D. Okay. In addition, we have some other interesting things. That means that these little angles here are the same size. In other words, angle B, this is A, angle B, A, C is congruent to angle DAC, which we could do that by measuring. Let's go ahead and do that. Let's see, let's turn these angles off, and let's just measure these two angles. So this angle here and this angle here. And if you look, they are the same size. And again, if we manipulate, they may be different sizes, but they're same size as each other, right? So we say that so that this bisects the angle here. And we're going to get the same thing at the other end. It's an angle bisector at both ends. Okay, and again, we prove that because these are congruent. Okay, what transformation will map this side, this triangle, onto that triangle? Can you figure that out? Well, it's a reflection. It's a reflection about this mirror line of symmetry that contains what we call the major diagonal. So just some terminology, the major diagonal of a kite is the one which is going to have on it the points where the two congruent sides meet. The minor diagonal is the other one. It has on it the 2 points where the potentially non-congruent sides meet. It's possible these two sides could be congruent as well, but they're not necessarily have to be, like they're different right here, different lengths. Okay, and so we can look at that diagonal. That's the minor diagonal. So right now let's focus back on the major diagonal. And if we look, the line containing the major diagonal is a line of symmetry. In other words, if we reflect over this line, A and C will be fixed points. They will not move. But what about B? Let's actually do it here using GeoGebra commands. Reflect about a line. We're going to reflect the point B about this mirror line. And look where it ended up. It ended up, they called it K7 here. Mine, yours might call it B prime. But look where it landed. It landed right on top of D. Let me get rid of that so we only have one name for it. Okay, so this is a kite we see that has a reflective symmetry about this line containing the major diagonal. It is a mirror image of itself, right? And so it makes two triangles that are congruent with a reflection. Okay. All right, let's go back to our tasks now. So we did that. We noticed the angles and sides. We noticed we had certainly congruent sides because of the definition. We had to compare congruent angles and make the major diagonal hide show. What do you notice about 3D triangles? We noticed that they were congruent. And we noticed about the angles formed by the major diagonal sides, that the major diagonal bisected the angles. And we were able to prove that by using the side-side-side triangle congruence theorem. Okay. Next, given quadrilateral EFGH with triangle EFG congruent to EHG, what type of transformation maps this? And of course, we saw that that was a reflection. And if you start with that reflection, it does have to be a quadrilateral. It does have to be a kite. And of course, the proof there is just notice that EF has to be congruent to EH. That's a pair of consecutive congruent sides. And then FG has to be congruent to HG. So that's another pair of consecutive sides for this quadrilateral EFGH. And so that makes that a kite. Okay, so notice that we have an if and only if thing here. A kite has the property that when you draw the major diagonal, it breaks it into two triangles, which are reflections of each other, congruent triangles. Okay, and we also have the converse of that, that if you start with a triangle, start with the triangle and reflect it over one of the sides, that outer part produces a quadrilateral, which has reflective symmetry, but it also turns out to be a kite. Okay, so at least in Euclidean geometry, the kites are exactly the same thing as those quadrilaterals which have reflective symmetry. All right, now here's the next thing. Do this set of do this set of constructions now. Now, after we've already proved this first, which is important, we do it in that order. Um, Now construct the minor diagonal and maybe make a hide show checkbox for it, checkbox, and construct the line containing the major diagonal. That was our line of symmetry we had a while ago. Not just the diagonal, but the line containing it. Construct the intersection of that line with the major that contains the major diagonal with the minor diagonal. Don't just construct the construction of the major diagonal and the line. So he can't make it into a concave kite and do it and make sure that it works. What do you notice about the relationship between the minor diagonal and the line containing the major diagonal? And then see if you can prove that, test out that conjecture and prove it. So notice we're doing something here that mathematicians do a lot. That you look at some situation, right? And then you maybe can look at an example, and then better yet, make some kind of dynamic example, say in GeoGebra, test out lots of conjectures, notice a property, test it out, see if it works, then actually turn your conjecture into a theorem or proposition by proving it. Okay, so see if you can do this yourself on the just constructions that you had, and then come back. Press pause now. Again, if you haven't done these constructions yourself, I strongly encourage you to do so. You learn a lot more by doing that than you do by just watching me do it. So here we have this. So now we construct our second diagonal, and it's even marked here. Let's call this point of intersection X. Made sure that I intersected this line with this side, not just intersecting this line segment with this diagonal here. Not a side, it's a diagonal. Okay, and so we get that, and if you notice, it's marked right here. You always get a right angle. And do you notice even anything else? Look what happens if we do this. Let's measure some things here. Let's measure the distance from B to X and from D to X. Look at that, they're the same length. Pretty clear that the distance from A to X is not the same as from C to X. Maybe we should notice something else before we even do that. If we take away the major diagonal and that mirror line there, and just look at the minor diagonal, notice that we have two triangles formed that way. Notice that these are not necessarily congruent, but they are isosceles. So among other things, that means that the angle at B here, the angle CBD, is congruent. Well, I'll just measure it here. The angle CBD is congruent to the angle CDB. And that one, we want to make sure that that one is between 0 and 180 degrees. And here I have a measured in radians. Again, you can switch it to degrees if you want. It doesn't matter. These are the same size. Remember, that's something we know about isosceles triangles. Okay, so now let's look at the major diagonal, or at least the line containing the major diagonal. And whether we're looking at this situation, oops, let's go ahead and turn that one back into between 0 and 180 degrees as well. And so now we notice that we have these some triangles here. Well, look at the triangle right here, triangle BCX and DCX. Well, we know that these two angles are congruent. And remember, because this is isosceles, you get these two angles are congruent. Okay, and so now we have enough, and of course CX is congruent to itself. So now what do we have? We have, well, we have side angle. That's not necessarily enough to make the two triangles congruent, except that we know, if we know that this is if we can know for sure that this was a right or obtuse angle here, we could get there from there. But if you remember, let's look up here at this triangle on this side here instead. Well, let's look down here. We have already proved that this angle right here and this angle right here are congruent. So we're talking about this angle right here being a angle between 0 and 180 degrees. Let's just make it a different color. Versus this other little angle right here. Let's also make it between 0 and 180 degrees. And we see that these two angles here are congruent. Where we proved that before by showing that these two triangles were congruent. So we did that first. So we got some angles here. So now we know for sure that we have angle, side, angle, and that is enough to make these two triangles congruent. Well, what does that turn out to do? That turns out to make these angles BXC and DXC congruent and a linear pair. That makes them congruent and supplementary, which means they have to both be right angles. So in fact, we prove that the line containing the major diagonal here intersects the minor diagonal in a right angle. It's perpendicular. Furthermore, when we look at this, we look at the triangle BXC, okay, and the triangle DXC. They're congruent, so that makes this BX and DX congruent, as we saw a while ago with our measurements. So in fact, these two triangles are congruent. So what this says is that the major diagonal, or at least the line containing the major diagonal, is a perpendicular bisector of the minor diagonal. Now, of course, it's perpendicular. The minor diagonal is perpendicular to the major diagonal, but it's not necessarily a bisector. Notice the way I've got it drawn right now, CX is quite a bit shorter than AX. So here we have one diagonal being a perpendicular bisector of the other. Now at this point, one of the things that you should ask yourself is, what about the converse? If we start with a triangle that has a diagonal that's a perpendicular bisector of the other, can you prove that it's a kite? Is it true or not? Or what if we relax that a bit? Do we need all of that? Can we just say, what if one diagonal is perpendicular to the other? Is that enough to make it a kite? What if you just say one diagonal bisects the other? Is that enough to make it a kite? Do you see how in mathematics, oftentimes if we come up with a theorem or come up with a conjecture, we prove it, we've kind of closed the loop, but then it's time to start the process again, because oftentimes the best time to work on a problem is right after you solved it. So here's an example of where we might take this and say, okay, what about some other things? What about the converses of this? Okay, what about converse, or what about some possible conditions? What happens if I put more or less? So for example, what if I relax the conditions? What if I only have one pair of consecutive congruent sides? Do you still get uh, get the results that we got here for kites? Yes or no? Make some conjectures, look at counterexamples, build them in GeoGebra, or if they're not counterexamples, prove that it goes the other way. And of course, another way we can go is do the same thing now in hyperbolic, spherical, and taxicab geometries and see if these properties work in those geometries as well. Okay, if you think about our proofs, perhaps this might work in Euclidean. It does work in Euclidean geometry. What about hyperbolic or spherical geometry? You may say, well, look at your proof and see if we used any steps that aren't allowed in those geometries. If not, then the same proof may work and we may get the same results. And of course, you can test it out with a GeoGebra construction as well. So I have here, let's see here, the properties of a kite. So let's just go over what we've discovered. A quadrilateral is a kite if and only if it has two disjoint pair of consecutive congruent sides. That's the definition. The major diagonal has endpoints where the congruent sides meet. The other diagonal is the minor diagonal. A convex kite is also known as a dart. That's just another name for a convex kite. The major diagonal and its sides form two congruent triangles. Specifically, if the way we've got it set up here, triangle ABC is congruent to triangle ADC. So it has reflective symmetry about the line containing the major diagonal. The major diagonal is part of an angle bisector at both ends. It has a pair of opposite congruent interior angles where the potentially non-congruent sides meet. In other words, the angles at B and D, the interior angles, the big angles there. The minor diagonal and the sides form two, not necessarily congruent isosceles triangles. The line containing the major diagonal is the perpendicular bisector of the minor diagonal, and the diagonals and the sides form two smaller pairs of congruent right triangles. Triangle BXC is congruent to triangle DXC. The order matters there. Triangle AXB is congruent to triangle AXD. So these two right triangles are congruent, and these two as well. Well, again, with a reflection. And remember, I asked you about some of those converses. Hopefully you stop and explore this on your own. But here's some things that are equivalent. Quadrilateral ABCD is a kite with AB equal to AD and CB equal to CD. That's equivalent to saying we have a quadrilateral with triangle ABC congruent to triangle ADC. If you have this two congruent triangles like this with a reflection, then it has to be a kite. If it's a kite, it's got to be this. So all these are sort of if and only if statements. Quadrilateral ABCD with AC being the perpendicular bisector of the minor diagonal, that turns out that's enough to make it a kite and to have these triangles that are congruent. Quadrilateral ABCD has a reflective symmetry about AB. That turns out enough to make all these other things true as well. And of course, we've already seen that that's true. We've already seen that if we have a kite, that it has a major diagonal being a minor, with the major diagonal being an angle bisector on both ends, or at least part of the angle bisector on both ends. We knew that that was a property. It turns out if it's got that property, then it has to be a kite. It has to have all these things. And we have quadrilateral ABCD with the major diagonal being an angle bisector on one end, and BD is perpendicular to AC. That's enough to make it happen, make it be a kite. And quadrilateral ABCD with the major diagonal being an angle bisector on one end and AC bisecting BD. All of these proofs boil down to proving that we have this pair of congruent triangles. So if we can take the congruent triangles and show that all of these other things are true, and then take each one of these and show that we have the congruent triangles, we've shown that these are all equivalent to each other. We'll look at that proof in our next video.